I'm starting to record right now. So this afternoon session on IoT Connecting Things is about serial interfaces. So practically what we are talking about here is how to connect devices, smart devices, with each others. And we start from the very beginning. RS-232, which stands for Recommended Standard 232, which is the so-called serial port of your computer. This is your grandparents' computer from 80s. So it used to have this 9-pin or 25-pin the serial port connector on the back side of the computer, which was also nicely heating the room. And basically it's a standard RS-232 compatible serial port. Early computers didn't have the integrated parts there yet, so there was separate card having the serial port interface. The origins of serial port, actually, it was the device that was designed to connect not a computer, but a terminal and a modem. So yes, computer and a modem too, but actually even with just a teletype terminal, you could connect a modem on it. And yes, it's actually introduced in 60s, so it's almost 60 years old already, 57 years actually, or 58 year of RS-232, and it remained a long time the default interface for many systems, and it's still in use in a lot of systems. And actually, it's still in use in modern computer systems. Many features, although around year 2000, USB started replacing this connection, but however, it's still visible in a lot of places. So what is all about? PC and modem. So practically in here, the modem was thought, okay, this is the communication equipment. So data communication equipment, DCE. And then the PC or a terminal would be data terminal equipment, DTE, where the PC is a dumb terminal and modem does all the work. We know that currently it's totally the other way around. But anyways, this is history, where it comes from. And actually, in order to control PC, so modem was controlling PC, there are some lines for signaling. So basically, signaling to indicate when line is up, modem is ready to transmit when there's some data available on PC and so on. So what the standard actually defines is the electrical characteristic and connectors, either the male or female. What kind of system has a male connector? So that's the dumb terminal. Female connector is on the that modem side, and so on. Electrical characteristics like the what is the voltage for? Logic state 1 and 0. And actually there's also idle, which is same as 0. But what it does not define is the encoding. What kind of encoding does it use? What kind of framing? It doesn't even dictate how many bits you have. It can be varying bits. It doesn't tell anything about the speed either. So it's just the hardware standard. So lowest level hardware standard for the communication. And here are the pins. Actually, the TX and RX are the only that carry the actual data. The rest of the pins are used for the flow control. So basically those 9 pins, it has common ground and then transmit data and receive data. But then also these handshaking signals, which are used mostly with the modem. On the other hand, to make a secure transfer of data between two PCs, these handshaking lines are actually quite handy. And yeah, and then there's the 25 pin version of the RS-232, which has also numerous extra signaling lines like the secondary data lines. Voltage levels. Okay, this is on cable, so cable between two computers. It uses plus minus 12 volt signals. And the low level actually is interpreted as logical 1 or idle. Idle means that nothing is being transmitted, but low level, actually the voltage level between minus 15 and minus 3 volts is logical 1, and the high level plus 15 to plus 3 is logical 0. So it's inverted in that sense. So higher voltage level means 0, lower voltage level means 1. But nowadays, say, typical microcontrollers operate mostly on the 3 volts. So it seems that we need a level translator, just like the left-hand side picture here. That's a standard RS-232 level translator. If you have a physical wire connection between two separate devices. Okay. So, but it's just connecting few 3 capacitors for 5 capacitors actually to the operating voltage, and then it just has the level translation on both ways. But this is more or less history, at least for you guys. But anyways, you need to understand the something like how these bits actually relate to anything. So typical transmission, and this is now on voltage levels. So we start on idle, meaning negative voltage. Start bit is 0 at the beginning. And then it's followed by 8 data bits. Okay, 1, 2, 3, 4, 5, 6, 7, 8. 8 data bits, and you're sending the least significant bit first, and the last one will be the most significant bit. And after that, you have a pause, meaning stop bit. 1 bit, 2 bits, or actually 1.5 bits is also used, since basically this stop bit is just giving some time for the transmitter and receiver to recover from the previous data. So this here sends from, we need to read it from here, most significant bit. Hey, wait a minute, this is least significant bit first. Just started thinking, was it least significant bit first, or oh, well, it says it here. So we have 1, 1, 0, 1, or actually we read it from here. 0, 1, 0, 0, and then 1, 0, 1, 1. So that's the binary code, which is, that's 8, and that's 8 plus 2 plus 1 is 11B, 8B hexadecimal. Okay, so this is how you read the data I'm not sure about the least significant bit first here though, but anyways, that's Juho's problem, not mine. Okay, so does not define how the data is actually sent, only the low level parameters. But basically the sending and receiving devices must have the same settings. Okay, how many bits? Number, usually 8. And the order of the bits in data frame, meaning which bit goes first. Common order, it says it's least significant bit first. And then speed. You know that 2400 bits per second was, at one time, it was called the fast speed serial line. We know that USB can do now a few hundred megabits per second in burst mode, in the super speed mode. So these are relatively slow, but well, you know, just like any technology, it started somewhere. And these are somewhat standard speeds. So from 300 to 115,200 bits per second. And yeah, those are the most common values. Although the hardware actually usually supports any number speed nowadays. So if you want to have, for example, 1645 bits per second, yes, you can put it, as long as both the sending and receiving end will have the same setting. Type and number of stop and parity bits. Okay, usually you have at least one bit. And parity checking bit, that used to be quite important. Nowadays, if you need to send data from one place to another, you don't use the RS-232 there if their data integrity is critical. But this is the common numbers nowadays are the 9600 bits per second, 8-bit data bits, no parity check, and 1 stop bit. That's what it says. So if you have, for example, 2407 002 would mean 2400 bits per second, 7 bits, odd parity check, and 2 stop bits. But anyways, you get the idea. That's the most common combination. There. So if you have this RS-232 without voltage conversion, it can actually be used, for example, between two microcontrollers which are practically within very short distance, where you can practically take a wire from a single wire from one device and connect it to the next one. Just like in this Tinkercad environment, if you put two Arduinos there, then you can connect the wires directly between TX to RX and RX to TX without any level translation. And then basically they are using the positive logic. So not inverted logic, but the normal logic. Idle meaning 1, which is around 5 volts. This is, by the way, again, Juho's home laboratory measurement. And here we have the start bit going 0, and then we have first bit 1 0 1 0 0 1 1 and 1 stop bit. Okay, then you can decode that down back to the hexadecimal or decimal number. That's binary number. Good. The following kind of signal on the bus. Yeah. Most of the computers nowadays don't have any RS-232 ports anymore, but there are this kind of small gadgets that are plugged into USB port, and they behave like RS-232 port. So if you have an old instrument, for example, with physical RS-232 connection, then you can buy this kind of adapter for €3, something like that. And this does all the translation for this physical line. And it looks like in Windows, it looks like a COM port, communication port. And in this case, it's A10 USB to serial bridge, which shows up in COM8 in your computer. And by the way, these ports, COM and LPT, has been there on PCs since as long as there has been PCs. The drivers act exactly the same. But now the drivers are virtual drivers. So this is a USB device, but it looks in computer as a COM port 8 with some flow control there. So that's the settings for that port. Bits per second, data bits parity, and then I have this annoying window there, one stop bit, no flow control. Okay. So in the end, USB serial port behave exactly like RS-232 serial port in computer. The Arduino ports or board has a built-in USB serial adapter. So when you plug in the Arduino to your computer, the computer recognizes two devices. One is the programming device to upload the this microcode from your PC to your device. And another one is this communication port. So those are connected to this Arduino. I think it was a digital line 0 and 1. Last week exercise, there was that communication port, virtual communication port there, and the monitor for the communication port, if you remember. Okay, microcontrollers on R2, and that's exactly what it is. The communication port for serial communication TX1 is on Arduino pin 1 and RX is on Arduino pin 0, which are actually physically connected to this small device here, which is the USB bridge, or actually dual purpose thing. So this processor is the actual Arduino Atmel AVR processor, and this is the serial interface for both that serial port and also to upload the program. In simple serial library, there is a software WART, software implementation. So this TX and RX are actually tied into certain pins on the processor, and if you use those pins for transmission of data, then you cannot use those for digital I/O, other digital I/O, of course. In case you need pins somewhere else, or in case you need multiple serial connections, then you need to actually have this software implementation of UART. Remember the speeds. Okay, let's take a look. In this speed, okay, we have 50 microseconds per division. So the bit width is just about that 50 microseconds. So my guess is that this actually has 19.2 kilobits per second based on this length. Now the data width. In 50 microseconds, you can do lots of the instructions. You get actually about 50 instructions during this line. So making a software transmission is quite simple task. You just need to time it correctly to send data, and you need to listen the input port at certain times to receive data. Sounds like doable with software using any microcontroller. You have access to timing and I/O. However, of course, when you make it the software, then it slows down and takes a lot of resources. So if you can tolerate using just one the RS line or serial port, that will be great, since then you can actually use this hardware inside of the microcontroller. Okay, Arduino software serial library. Last time we had the Arduino, the serial port in example communication port. Now we have the software version here. There are some limitations. If the multiple software serial are used, then only one can receive data at a time. Receiving data does not work on pin 13 for some reason. Maximum speed 57.6 kilobits per second. Although the processor itself could easily handle also that 19.2. Oh, that's actually, this is 4 times that. Yeah, sorry, forget it. I was about to tell you something stupid. So yeah, 57.6 thousand bits per second. Not too high frequency. And then there are these other Arduino boards. There are Mega, Micro, Leonardo, you name it, different variants, and these third-party Arduino compatible things, they have different limitations too. But let's take a look at what kind of functions it has. So we have function software serial available begin, and practically it has the same functionality as the serial port, only that this is now running a software. And there are some examples there, schematics, code there. So defining the pins. So basically, software serial, my serial 2, 3 defines my serial function as the serial port, and here okay, software serial, which is software serial. My serial, okay, there. There is where you set your my serial to 38,400 bits per second, and that's just printing hello world, and so on. You can read yourself. There. So works the same way as the Arduino hardware, but now it also takes resources from the software. Okay, so using the software serial request, including the header files, include software serial.h, creating my serial object. You can name it as yourself, as you wish. Two parameters, which are the receive and transmit pins in that order. And then you need to, on setup, start that software, the serial, by telling what is the speed, and then write or read from that serial port. Then it works just like the serial line it should work. Good, simple, and even with some demonstration. Okay, this banner is really annoying. Oh, great. There we go. On Tinkercad. Let me copy and tinker. On one session when I did that one, for some reason Zoom stopped working. Let's see if it happens also now, since it takes for a while there. Okay, I think this is okay. Good. So we have two Arduinos, meaning that we have code for both. So this is Arduino number 1, and the code has the software serial on pin 2 and 3, transmit on pin 3. And here we have that line actually transmits from this device, and the second Arduino is reading it. Then we have this setup, pin mod 13. Well, output it's not used, but it looks like it's still there. Doesn't matter. We start the real hardware serial part, and also the start that on my own serial 2 software port with different bit rates, initiate a variable val, and just start printing different numbers of that value at rate. Okay, that's about 10 10 times per second, and increases the value in between. So it starts from 0, and then actually, yes, then it goes and prints that. And print ln actually does so that it sends characters. It sends actually the value in as a string. The second is the receiving then. Okay, yes, software serial, the same code. And then basically also defines that serial 2 line is listening. It starts it and starts listening and waits if there is a byte available in software serial line, then it reads it, serial to read, if the byte is available, and just prints it on the hardware serial port. So the nice thing about the hardware serial port that you can actually have the serial monitor showing what is happening. See, let's turn on the serial. Okay, it's there. When I start the simulation, let me put a little bit more delay here. So 1000, so 1 second delay in between. So the sending happens there. 1, 0, 1, 3, 4, 5, 6, 7, 8. The oscilloscope just doesn't quite work there. And then that actually what this first one is sending, and here we have what the other one is the receiving. See, the delay is slower. Actually, it doesn't need to have any delay, and it receives the same values as the first one is sending. Okay, nice. That's really nice. Okay, let me go back to that one. Arduino Uno and one, and I will be sending. I'm just checking something here. Serial 2. If I send 0x0 1, I want to see which bit is actually least significant. Cannot say since this is not binary. Sorry, forget that one. But anyways, one is sending, another was receiving, and they are actually now sending and receiving the characters, like in text. So sending value 0 means that it sends a character which represents 0. All right, so back to the business. That RS-232 had a KVAT on the signal line length. It really doesn't work in longer than, say, within a room. So up to 50 meters max. And then basically you will get into some trouble, mainly due to the cable reflections and nasty stuff like that. To overcome that problem, there is actually RS-485 standard. Again, it's an electrical layer standard, the hardware layer standard. But this one actually overcomes the problems on the length. So it's a long distance cousin of RS-232. And yeah, maximum distance for RS-232 is about 50 meters with that line buffering. If you go to, let's see, can I change? Oops. If I go back to this, in reality, this kind of lines, maximum, say, few tens of centimeters without that line buffering. With the hardware line buffering, this would be, say, that within 50 meters. That actually, that 50 meters is longer than USB. In USB, standard defines that you cannot have longer than 5 meters of cable. You cannot, unless it's a non-standard design for that USB transmission, or actually then it's a kind of bridge using some other than USB technology in between. Okay, so back to this business. So 50 meters. Okay, there are a couple of things in RS-485. The signal is differential, meaning that it's actually the a difference between two lines, voltage lines. And here we have the mark and idle state. And the signaling here actually goes, or actually mark 1 or idle, and space is 0. Okay, so we start from a slightly positive line on one end and slightly negative on another one. Then we have a strong start signal by giving the space state, meaning logical 0. Then we have this couple of marks, 2 spaces, mark space, 3 marks, and releasing in an idle mark. Okay. Doesn't seem much, but practically we can, with this RS-485, it's a twisted pair wire, which basically, if you put that one in a noisy environment, like next to electric lines or next to power supplies, next to anything, there will be a voltage, the noise in that wire. So practically any distance wire works as an antenna. Longer the wire, then more this extra signal you will get. But if you have twisted pair wire, they're on the same medium, so practically even though both will get some error, they will cancel out on the difference signal. So practically RS-485 is now much more immune to the interference as than the RS-232. And that how the maximum speed for short distances without any extra termination is about 10 megabits per second. So similar length, 50 meters, but with RS-485 will give you, you know, 100 times better the data transmission speed. And actually you can take that wire up to say 1 kilometers or so. This similar technology with some small details is used on these DSL lines. So the telephone line, the copper cable, if you still have them, well, your parents or grandparents have it. Twisted pair, which means quite immune to any the interference. And practically, I used to have DSL line at home. As I said, I live on countryside, and there was something like 2 kilometers to the nearest the telephone switch station, switch box, and I got something like 4 megabits per second signals because of similar technology. Okay. But anyways, the RS-485 is kind of Ethernet, in sense that now you have a line that you can that you connect multiple devices at the same time. But typically up to 128. There's a good reason for it, but anyways, the 128 are the devices, which is quite a lot on one single line without any boxes like the bridges and the other stuff, switches. So practically this 485 line were the first high-speed local area network lines. Okay, the only requirement in the physical implementation is the 120 ohm resistors in both ends of the bus. And that actually is the terminating resistor that will stop ringing of the line. We are not covering that how that actually where it comes from, but you will get an idea on this material what we have here. And okay, there are these two data lines, and then there should also be common ground amongst among the devices, which might be actually a problem in some cases. But anyways, this transmission line should have a common ground. Good. And an example of nice RS485 transceiver. Okay, since it's a differential signal, you can actually drive it with a single ended the power supply, because you can put the differences either positive or negative depending on these depending how you switch these gates. And okay, there's a receiver and transmitter, and both actually have the well, the output has to enable, also input has to enable, then digital or the data goes into that circuit, or then the received data comes on this pin, and those are the differential lines A and B connected to the wires. And oops. TTL level data input and output. TTL level means what we have earlier. So TTL high level is above 2 volts, low level below 0.8 volts. Okay, so that's kind of historical things. Although this RS485 is basically the next step from that one is the local area network Ethernet. It uses the similar technology. It also have this terminating resistors, and it also uses pair cable. It also uses these unipolar powers. So lots of things are in common. So next, what to send or how to send data on serial line. On that Tinkercad example, the value was sent as ASCII code and or text, and basically that communication kind of thing is based on so-called ASCII characters. What are the ASCII characters or character set? So on the beginning, when the bits were made out of wood, oh boy, it was fun carving out of the wood on our cave where we were living before the computer. Okay, so the early days of communication, no standard way of encoding characters to numbers or bits. And there are few different competing ways of doing it. So there's so-called Bardot code, EBSDIC. Actually, I have been working some exercises with EBSDIC coding. That was in 80s, not fun. Telegraph codes, there's a Bell code. There's a plenty of different ways of encoding characters to numbers of bits. However, the telex system actually was one of the real users of numeric encoding. Telex was worldwide kind of agreement of how to send text and sending using telephone line to remote location. So one transmitter can send to multiple receivers. So for example, how to spread news over the world without modern communication channels using just telephone lines and switchboards. You have one sending telex machine sends characters and these are typed in one end. Okay, that's where everything actually started. Then there was the American Standard Code for Information Exchange, which comes as an ASCII, and that's also 57 or actually it's 58 year already. It started then and it's still most dominant character set. The current character set, ASCII code is 8-bit. The current character sets are like Unicode, that's 16-bit characters, but it still is based on the ASCII code. So yeah, standardization happened in America. And there you have a teletype model 33. On left hand side, there is a telex machine that's sending characters, and on right hand side, there is a teletype receiver. So you can see it doesn't have the dial button, this dial where you actually select the telephone number of the receiver. And practically here you just type tick, tick, tick. So where do you put your memory card? No, you don't put your memory card. You have the text on one hand and then you do the one finger system on that typewriter. History. And this is the code, ASCII table. You took some time to find the Creative Commons table on ASCII characters. And that's why I think this is it on Spanish or is this Portuguese? I have no idea. It's actually a mixture of English and maybe Spanish. So for example, there's a null character, caractère nullo, and so on. And when we go, so we have lots of special characters here, which does not actually print out. On here, on this decimal number 32, 20 hex, that's espacio, meaning space character. And then we have special characters starting from decimal 48, we have 0 to 9. Okay, those characters. Then we have a couple of extras, and then the uppercase characters start from A, from decimal 65, and then ABCDF and so on up to Z. Then some parentheses, and then again decimal 97 starting is the lowercase letters. So in between here is actually 20 hex. But anyways, so it has characters that print, and then printable characters, and then there are non-printable control characters. So, and some of these are quite fun, like decimal 7, bello. That actually sounds bing on your terminal when it receives it. It should still work on these virtual terminals if they are ASCII compatible. Okay. Another things, those are the characters. Then there are a couple of things from the typewriter, like decimal 10, line feed. Line feed means that you go to the beginning of the line. Then carriage return, meaning that you will twist that on the lever on typewriter, which means a change of line. So basically, to make new line in, or the go to a new start of the new line in ASCII terminal, you need to send line feed and carriage return. So decimal 10 and 13, I think usually it's carriage return, line feed, in that order. Number 13 and 10. Wow. Do you need to actually remember this? No, you just need to understand it. Extended ASCII, as you saw last, this original ASCII table, it's American. Americans don't use these umlauts, any the markings on the top of any characters, unlike the rest of the world. For example, this Spanish has this A with a prime on the top of it, that kind of things. So where are the Scandinavian characters? Well, ASCII takes only 7 bits. When you add the 8th bit, it basically means another 128 characters. So, for example, the Scandinavian character set can be found from there. I can find as decimal 147, and then yeah, is 229, and there are also some other kind of like this A with E umlaut, or German Ü is here, and so on. So this is for, say, European character set, and a couple of other special marks, like the some 3/4, it has a separate mark, half has a separate mark, 1/4 has a separate mark. What else? This legal sign and some mathematical symbols already there. Registered mark, copyright, that kind of characters are there. Okay, this is something that you sometimes need, the degree. It's decimal 167. Great. So anyways, character set a Scandinavian character set is on the higher 128 character set. Good. Some history. And those are the characters, period. Plus Unicode, which has another byte more. The extra byte there tells you which region are you on, or which language region. So practically then you have plenty of different the character sets there. Almost enough. About the ASCII set, the first 32 non-printable characters are actually mostly to control the displaying device, like that bell ring. Hexadecimal 7, well, that's the same in decimal. Bell, a signal means the receiving device must ring a bell to make a sound. And then we have carriage return, line feed. Carriage return is 0D hexadecimal, and then line feed 0A hexadecimal. And so if you take and type something on, for example, Notepad here, and break this file, open it with a file editor that can show you what are the real contents of each byte on that file. This file, we can see that actually this is the A test file. The first data on that file is number 61 with this lowercase a. Next one is 20 with this the space character. Then we have T with the 74, then E 65, and so on. So these numbers here actually these are hexadecimal numbers, show the binary number of the corresponding letter. So where's the beef? Currently, Word is slowly moving to different standard UTF-8. And by the way, UTF-8 is ASCII. So it's exactly one-on-one copy on that one. If we are taking the UTF-16, then it's different on the higher byte, but not on the lower byte. It's still ASCII. Wow, another demonstration. Looks like the same, but actually this one has a twist. Let's see if I can. There. Oh, that's annoying. That is really annoying. Ah. Okay, let's see what happens, if anything. Loading, loading, loading. Looks like the same, but now, let's see. Previously we sent data. Okay, that was val. With print line command, which is formatted print. In this example, we are writing the value. So writing the value, and actually we start with value A, character A. Let's take a quick look at this ASCII table. Looks like Juho is also at the, just about at the same place. Presenting ASCII table. Decimal 65 is character A. They are the same. Like in here, it doesn't make any difference if you are using that value, integer value of character A or integer value 65. And by the way, you could use short integer values here, since this serial write command is actually sending 1 byte at a time, or an array of bytes. Okay, so these are equal, either character A or decimal number 65. That's A. So here we serial write on both the monitor and on software line that value, and then we increase the value until we hit the age, and then we start over. And maybe I will have that 1 second delay here again, and see on the receiver the same thing. It receives the data at 2400 bits per second, waits here until the data is available, and then serial write the value. So it writes the binary value. So binary value. So if I start simulation, it should start sending bytes. Okay, here you can see serial monitor A, B, C, D, F, G, H, A, B, C, D, E, F, G. Okay, so basically it works like that. Let me stop the simulation and maybe make it a little bit faster. 10 characters a second, just to see. Okay, now on that display, function generator display, you can see characters A, B, C, D. Okay, B, C, D, F, G. Quite fast going. It looks like it's the least significant bit first. Look how this, maybe I will show you this one in detail. So we have characters from 65 to 70 something, decimal numbers. The most significant bits on that data do not change. Only the least significant bits will change there. Something like three last digits are changing. On the other hand, this oscilloscope in this the Tinkercad it's not an optimal, let's put it this way. Okay, so ASCII is still with us when you are sending the data so that it's a terminal that prints out, or something that human can read. you can send data in as an ASCII. On the other hand, those Arduino, when you print line, then you actually read characters. When you send a byte, then it's write character, and then let's see, was it write and read? Yes, read characters, maybe, yeah. So, but anyways, the ASCII code, it's still in use, living strong. Okay, and we had this demonstration. How about having a break? About 5 minutes break. If you have any questions, please ask now.